Dear students, in the last video we have discussed how addition reaction takes place, then types of addition reactions, that is ionic and radical depending upon the reagent first added or the part of the reagent first getting added to the multiple bond. Then we have discussed electrophilic addition reaction. Electrophilic addition reaction, how it takes place. Then addition of symmetrical reagent on with the symmetrical alkene and unsymmetrical with unsymmetrical alkene, where we have discussed Markov-Nikov's rule. That means how a unsymmetrical reagent adds to a unsymmetrical alkene, which rule actually it follows. Then we have discussed the conditions or the requirements for Markov-Nikov's addition, and there are some examples also we have discussed which are anti-Markov-Nikov, and in some cases also we have discussed how an unexpected product is getting formed in the cases where there is formation of carbocation rearrangement and there is a ring expansion. In this video we will discuss the stereochemistry of addition reaction. Stereochemistry of addition reactions to alkenes. Those who want to know about Markov-Nikov's rule, how the addition takes place following Markov-Nikov's rule, and the cases where the addition becomes anti-Markov-Nikov, and also in the cases how the unexpected product is getting formed as a major product. Those who want to know, they can see my first video on addition reactions. Now let us today start about stereochemistry of addition reactions. We know any reagent which is going to add to a multiple bond, we know it is called generally addendum, and it has two parts. One part is electrophilic or electrophile and the other part is nucleophile. For example, HCl. We know HCl bond is a polar bond, so H contains little positive charge and Cl contains little negative charge. Therefore, H plus is the electrophilic part and Cl minus here is the nucleophilic part. Similarly, HOCl, ClOH. Here Cl contains bit positive charge and oxygen contains little negative charge. Therefore, here also this Cl is the electrophilic part and the OH minus is the nucleophilic part. Therefore, any reagent which is going to add to the multiple bond has two parts. One part is electrophilic and the other part is nucleophilic. You may be asking, when we are considering a bromine molecule, here what happens, both are similar atom, therefore there won't be any polarity. This is a non-polar bond. But when it approaches a multiple bond, slowly the atom which is close to the multiple bond, the electrons of that side, the electron cloud gets repelled by the multiple bond. Therefore, the cloud becomes like this. The electron cloud becomes like this. So the bromine atom where less electron comparatively is present, that becomes little positive and the other one becomes negative. So the non-polar bond becomes polar when comes in contact with a multiple bond. Now this part becomes the electrophilic part and this part becomes the nucleophilic part. Therefore, whatever may be the reagent which is going to add to a multiple bond mainly has two parts. One is the electrophilic and the other part is the nucleophilic part. Now, when both the parts join from the same side, let this be our multiple bond. When the electrophilic part E plus and the nucleophilic part, when they add from the same side, so if this joins from this side, this also joins from this side, or they may join from the same side. Both will join from the same side, either from this side or from this side, then such a addition is known as syn addition. Such a addition is known as syn addition. If the addition is like this is the multiple bond. If one part adds from this side, let the electrophilic part adds from this side and the nucleophilic part adds from this side. Or we can do like this, electrophilic part add from this side and the nucleophilic part adds from this side. Such addition is known as what? Anti-addition. So the addition is of two types, syn addition and anti-addition. And the addition is here is always stereo specific. Addition is stereo specific, both syn and anti. Both syn and anti-addition is stereo specific. What is stereo specificity? When the reaction mechanism leads to different stereoisomeric products, different stereoisomeric products from different stereoisomeric reactants. Stereoisomeric reactants, then we will say the reaction is stereo specific. So here both syn and anti-addition, both additions give are stereo specific. That means a particular stereoisomeric reactant will give a particular stereoisomeric product. Let us first discuss about syn addition. We have two types of reagents where the electrophilic part is not equal to the nucleophilic part. That is the reagent like HOCl. So here Cl plus is the electrophilic part and HO is the nucleophilic part. So if the reagent is like this, or HCl also you can take. So if the reagent is like this, then how the syn addition will take place and what is the product we are going to get, let us see. Here let us take the alkene. Alkene is like this, C double bond C, then CH3H, CH3H, and this one we know cis alkene or cis 2-butene. Now this cis 2-butene to this, when such a reagent is getting added, for example E plus and Nu minus, reagent of this type, then what is the product we will get? The product we will get here is, let us write like this, CH3, H, E, Nu. So this is because here two hydrogen atoms, these are two chiral carbon atoms, and here two hydrogen atoms are on the same side. So it is called erythro. It is called erythro. We know when two hydrogen atoms are on the same side, it is called erythro. From saccharides, the name has come, erythro sugar and erythrose and threose sugar. When two hydrogen atoms are on the same side, the sugar is known as erythrose sugar, and two hydrogen atoms are on opposite side, this side or this side like this, then they are known as threose sugar. Like from that this name has come. Here the two hydrogen atoms of these two adjacent chiral carbons are on the same side, therefore it is known as the erythro. So when there is syn addition from one side, let us consider the addition from this side, or in black lines I am showing you from this side, from the same side, then we are getting the erythro compound. Now let us see here how we will get this compound. How you will get the name, how we will make the addition, mechanism of addition, let us see. We have the alkene like this. So let us draw the alkene like this. Let us draw the alkene because it is cis alkene. So let us keep the two methyl groups on the same side. Now the addition will take place from same side. So let us do one thing. From this side, addition, same side. Let us consider this side. So here, if addition will take place, then for example, electrophile will add here and nucleophilic part will add here. Then what will happen? The product what we will get? The double bond will become single bond. Now as it is, you keep here CH, this is CH3 and this will become nucleophile, and here also this is CH3 and this is H and this is the electrophile. Now to get the structure, this structure, what you do? Since it contains a single bond, no rotation is possible. It is a conformer and we can write its other conformers also. So here, since in this structure CH3 are on the two opposite sides, so let us will arrange or we will give rotations to this molecule in such a way that CH3 will come down. So let us rotate by 120 degree, this one 120 degree, this one also in the same way 120 degree. So if we rotate, the molecule will look like this. It will look like this. CH3 will come here, Nu will go here, H will be here. Similarly here CH3 will be here, then E will be here and H will be here. Now you can write the Fischer formula or Fischer structure. We can draw it like this. When we are converting a Schwarz structure to Fischer structure, always you know the groups which are down here, they will be, one will be at the top and one will be at the bottom. Then left side two hydrogen atoms, so keep two hydrogen atoms here, here nucleus and Nu and here E. Now if you see, this is exactly coinciding with this structure. So in this way, if we forget also, we can do the addition, because general students are getting confused whether we will get 3O or erythro. So simply by following in this way, we can arrive at the required answer, that is cis will give cis alkene on syn addition will give erythro. That means cis on syn addition we are getting erythro addition product, cis on syn addition. Now when this happens, when our reagent is like this, ENU, this is what? Unsymmetrical. When the reagent is unsymmetrical, we are getting the erythro product. Now let us see when the reagent is symmetrical, what happens. So symmetrical molecules are like hydrogen, bromine or halogens, etc. In this case, what happens? So again let us take the cis molecule, cis alkene, and this cis 2-butene. Earlier we have taken 2-butene, so let us take the same 2-butene and we will add bromine molecule. So from the same side, we will get the similar product. This will be CH3, this will be CH3, this will be H, and here the electrophilic part is bromine and the nucleophilic part is also bromine. Now if you see here, these two are chiral carbons. This is a chiral carbon, this is also a chiral carbon. Rotation of, see, this is a plane which divides the molecule into two equal halves. So the rotation caused by half of the molecule is cancelled by the other. That means it is a meso compound. Clearly it is a meso compound. So when in cis molecule, when addition is syn, we are getting a meso. So this we can remember like this: CSM. Cis, C for cis, S for syn addition, M for the resulting compound, that is meso. Similarly, if our alkene is trans, so if the alkene is trans, let us take trans 2-butene CH3H. So this is trans 2-butene. Now this trans 2-butene, when an unsymmetrical molecule, like let us take same HOCl, del plus del minus, when the addition is syn, we are talking about syn addition. So when the addition is syn, we will get the other isomer. The isomer will be like this: CH3, CH3, H, H, E, Nu, or here Cl minus, here OH, or Cl and OH. So this is, here two hydrogen atoms are on the opposite side. So this is nothing but the 3O isomer. So here we will get two products, 3O and its enantiomer. This compound and its enantiomer, where you will find this hydrogen this side and Cl this side. So let us draw it. We will get a mixture of two products here. So CH3, CH3, Cl, H, H, O, H. So this is also 3O. So this is a pair of enantiomer. It's a pair of DL pair we will get. Now, if the addendum is symmetrical, then what will happen? This is the alkene. This is trans 2-butene, H, CH3, trans 2-butene, and addendum is symmetrical, means bromine molecule or hydrogen molecule like this. If it is bromine molecule, then the addition product will be like this. Here we will have CH3, here we will have CH3, and here bromine. We will get bromine here and two hydrogen atoms, and its enantiomer both will be 3O. Its enantiomer will be Br, H, H, Br. So if one is a D, the other one will be L, and this one is L, the other one will be D. So we will get a mixture of these two. If you want to know how the addition takes place, let us again see the mechanism here. The addition, as I told you, we are talking about syn addition. Now let us take again in this way, let us draw the structure of alkene in this way. If you want to understand more clearly about the product formation, let us draw the structure like this. Then on syn addition, syn addition, let us consider addition from this side. So one bromine will add from this side and another bromine will from here to this carbon. As a result, what will happen? Well, this structure will become like this. I am omitting the carbon atoms. So this will be CH3, Br and H, and here this will become Br and this will hydrogen and this will be the CH3. Here what happens? The trigonal structure, because sp2 carbon is trigonal, it is getting converted to tetrahedral, because here the sp2 carbon changes to sp3. Therefore, its structure is tetrahedral. So it becomes like this. Now what we do? To convert into Fischer projection formula, as I have done here, I have written here, let us give rotations. This rotation give 120 degree, and this one let us give same 120 degree rotation in this direction. Therefore, we will get here the corresponding structure here like this. This structure will be like this. CH3 will come here, bromine will go here, and hydrogen will be here. Similarly, here we will have CH3, and here bromine, and here hydrogen. That means its equivalent Fischer projection formula is like this: CH3, CH3, Br, Br, H, and H. So this is nothing but one isomer of 3O, either D or L. And we will get the other isomer if the addition is from this side. Both are syn. This is syn addition, this is also syn addition. But if the addition is from this side, we will get the other isomer as the product. So it will be like this. Its bromine will be here, hydrogen will be here, its bromine will be here, hydrogen will be here, and this will be CH3, and this will be CH3. As a result, we are getting a mixture of two isomers, as I told earlier here. So this is a DL pair. Now we have discussed the syn addition. The summary is like this: if the alkene is cis and the addition is syn, with a symmetrical reagent, we generally get the meso compound, which is optically inactive, and with an unsymmetrical reagent, we are getting erythro. We are getting erythro. No, but if it is a trans alkene and addition is syn, in both the cases we are going to get 3O isomer. 3O isomer. How we are getting in both the cases 3O? You may check, this is for your work, or otherwise you comment me, I will give the explanation. Now let us talk about anti-addition. Cis alkene on anti-addition. Anti-addition of a symmetrical reagent will give a racemic mixture. If the reagent is symmetrical, we will get a racemic mixture. So let us see how a racemic mixture is getting formed. The cis alkene, let me draw like this: CH3, CH3, H, H. So here the symmetrical reagent, let us take the symmetrical reagent as bromine. So here we will get CH3, CH3, bromine, here H, here bromine, and H. And the other one will get here CH3, Br, H, H, Br, CH3. So if here one is dextro, the other one is levo, that means the mixture is racemic, or we are getting a DL pair here. Here we are talking about the anti-addition, that means one from upside and one from the lower side. So here this is also known as what? 3O isomer, because two hydrogen atoms are on the opposite side. Similarly, if a unsymmetrical molecule or reagent is getting attached, we will get here unsymmetrical means we can write here like HBr. HBr means we will get the product like this: CH3, CH3, here and not HBr. Let us don't take HBr because one chiron will become achiral. So again let us take same HOCl. So Cl minus plus O minus. So here hydrogen, hydrogen anti-addition. So one side will be Cl and the other side will be OH. So here we are getting again two hydrogen atoms are opposite. When two hydrogen atoms are opposite, we are getting 3O. So this is the 3O isomer. 3O means always we will get two products here, and it's enantiomer. One is one isomer and the other one is its enantiomer. So 3O and in its enantiomer. You can examine these products as I have explained earlier by showing the addition and stereochemistry. You can do that so that you can know what are the actual products or the structure of the products. You can easily understand. So in this way, if our alkene is cis, can take C for cis, and addition is anti. So let alkene is cis, addition is anti, addition is anti, then the product is racemic. So this is abbreviated as CAR, C-A-R. So cis alkene on anti addition gives a racemic product if the reagent is symmetrical. Remember, if the reagent is symmetrical. Similarly, in short you can write, if the reagent is if a transalkene, for example here, transalkene on anti addition, we will get a meso product, as we have done in the case of cis, and similarly you can do here. And this is explained as TRAM. TR is for trans, A is for anti-addition, and M is for meso product. So you can easily remember by CAR and TRAM. Cis, anti-addition, racemic. Trans, anti-addition, meso. So if you once you know about the products of the anti-addition, then for symmetrical addition you will just interchange the products. In symmetrical addition, what will happen? You will get it is CS, M will come here. So CSM. So here trans, and if the addition is syn, then we will get the racemic product. So here we will get the meso product, and here we will get the racemic product. Now I hope I have given a clear-cut explanation of addition of or stereochemistry of addition of symmetrical and unsymmetrical reagents to a multiple bond. That is about syn addition and anti-addition. Now let us take a few examples. Osmium tetroxide, some reagent osmium tetroxide in the presence of sodium bisulfite always give syn addition. Syn addition of two OH groups. That means when you are seeing an alkene and you are seeing this reagent, you can easily know that two OH groups will be added to the multiple bonded carbon atoms. For example, if we have CH2, or we can write here RCH, CHR, let this be multiple bond, and the reagent is this, and the reagent is this, NaHSO3. Then you can easily write the product, that RCHOH and similarly RCHOH. So the two OH groups are on the same side, that addition is syn addition. Similarly, if the alkene is treated with KMnO4 solution, then again here also two OH groups will be added to the same side. You will get the same product, ROH. Syn addition will take place. If the reagent is bromine in carbon tetrachloride, a non-polar solvent, bromine in carbon tetrachloride, then the addition will be anti-addition. The addition will be anti-addition of two bromine atoms. Okay, so In case of osmium tetroxide and potassium permanganate, we are getting syn addition of 2 H groups, and in case of bromine in carbon tetrachloride, the addition takes place in anti. Now hope you understood how the syn and anti additions takes place in an alkene, in cis and transalkenes. In the next video, we will discuss about some important addition reactions of alkenes. Hope you understood. Thank you and keep watching my videos.